Hi, everyone. Let's say you want to solve this quadratic inequality, x squared minus 9 is greater than or equal to 0, but you don't want to think in terms of graphs. You're more of a numbers person. All right, so let's think about the real number line. For what real values of x will this left side be positive or 0? Now, a rational function can only change sign at its zeros, at the real zeros, which correspond to the x-intercepts, or where it's undefined. That is, where the graph has a hole or a VA. So for example, on the left, we have the graph of this third degree polynomial, y equals this third degree polynomial. It's a snake, a rising snake in this case. Now, there are two zeros, as it turns out. Over here and then over here. We have two real zeros. Now, these two real zeros are the only places where this polynomial function can change sign. Okay, so for a polynomial function like this cubic, the real zeros, which correspond to the x-intercepts, are the only places where the function f can change sign. A lot of writing there. Right. So for a polynomial function, the real zeros, which correspond to the x-intercepts, are the only values of x where the function can change sign, but it doesn't have to. Okay. So over here, at this real zero, this x-intercept, the function does change sign from negative to positive. Basically, you change sign when there's a cut at the x-axis. You change a sign when the graph cuts through the x-axis. Here we're cutting through from negative y-coordinates to positive y-coordinates. But then at this x-intercept over here, which corresponds to a real zero, we get a bounce. We don't get a cut, we get a bounce, which means that we don't change sign. For these values of x, y is positive, and for these values of x, y is positive. So for a polynomial function, the real zeros, corresponding to the x-intercepts, are the only places where the function can change sign. You get a cut here, but it doesn't have to. You might get a bounce. Now, if you have a rational function in general, well, again, it could change sign at x-intercepts or real zeros, but you can also change sign where it's undefined. So for a rational function in general, like for the reciprocal function given by 1 over x, here's a graph of y equals 1 over x. Here, we change sign across the VA. The function value is negative here. We have a VA like a river when we cross the river. Here, because the exponent on x is 1, it's an odd VA. So when we have an odd VA, when the exponent on the factor down there is odd, then we have a change in sign. For an even VA, we don't have a change in sign. Remember, y equals 1 over x squared. Sorry, y equals 1 over x squared. All right, we don't change sign. Positive here, positive over here. That's if we have an even VA. Here we have an even VA. All right. Also, you can change sign potentially at holes that happen to lie on the x-intercept. Although, again, you don't have to. All right. So again, where can a rational function change sign? At the real zeros or where it's undefined, like if you have a VA or a hole. But you don't have to change sign. You could have a bounce here, for example, or you could have an even VA, like over here. All right. So based on those principles, find the real values of x squared minus 9. Well, for the 10 millionth time, we get negative 3 and positive 3. These are like gates. They're like gates. We might change sign or we might not. Okay. So consider the real number line. Okay. X squared minus 9 can change sign at -3, and it can change sign at 3. We know that these are zeros for x squared minus 9. This is the sign of x squared minus 9. It's 0 at -3 and at +3. And then you can test values. You know the domain of a polynomial function is assumed to be all reals. We have 3 windows here. 3 windows. Bear in mind, for a general rational function, anytime you have a place where the function is undefined, you need another fence post. Here, we just have fence posts here where the polynomial is 0. If you have something like 1 over x, for example, you need a fence post at x equals 0, where it's undefined. All right. Now, in the test value or test window method, remember, x squared minus 9 only changes sign, potentially, at the real zeros. So test a value. For example, in the left window, test a value to the left of -3. For example, -4. Put a star here, -4. Although sometimes it's easier to use a ridiculous number like -1,000,000, right? But let's use -4. Plug in -4 into here, into x. What do you get? You get 16 minus 9, which is +7. I don't care that it's +7. I just care it's positive. I don't care it's +7. I just care that it's positive. Now, because x squared minus 9 is positive in value at x equals -4, it's positive in value all throughout this window. Because if it changed sign, we'd need another fence post. All right. We know it's 0 at x equals -3, x squared minus 9. What about here? 0 is the obvious test value for x. Plug in x equals 0, we get -9. That was why on that graph, 0, -9 was the vertex of this red parabola. All right. But I don't care that it's -9, I care it's negative. That's the key thing. The value of x squared minus 9 is negative at x equals 0. Therefore, it's negative at all other real values within this open interval between -3 and +3. So at x equals 1, 2, 2.5, -2.5, I know the value of this is negative. What about over here? Let's test +4. Or we could be cute and test +1,000,000, not to scale. +1,000,000. Plug in +1,000,000 for x. Obviously, 1,000,000 squared minus 9 is positive all throughout this window. And again, we're solving this inequality. X squared minus 9 is greater than or equal to 0. I want to know where x squared minus 9 is positive or 0. I'll put this in purple. I want to know where x squared minus 9 is positive or 0. I like it when x squared minus 9 is positive or 0, not when it's negative. I like it when it's positive, 0 or positive. So I want all these values of x over here, the left wing and the right wing, which corresponds to the same answer as before. It better. Method 4 is like a mix of like the sign chart method and the test window method. So here, I'm plugging in test values for x, like -4, 0, and +4, or +1,000,000 maybe. But remember, I don't care about what the actual value of x squared minus 9 is. I just care about the sign. So you might want to consider the factored form, the factor x plus 3 times the factor x minus 3. For example, if you plug in x equals -4, or even more easily, x equals -1,000,000. We know that a -1,000,000 plus 3 is negative. -1,000,000 minus 3 is also negative. So when you plug in x equals -1,000,000, or x equals -4 for that matter, we're going to get a negative times a negative. That result is positive. Again, this is a hybrid of the sign chart method and the test value method I just mentioned. Repeat the process. Again, we care where the product, x squared minus 9, which was this times this, we want where it's positive and where it's 0. Not where it's negative. We want where it's 0, where it's positive, and again, we want the wings. Again, we want the wings, which was this set over here. Okay. Next up, some more examples.